We're going to consider a couple of problems involving the photon emission spectrum of the hydrogen atom. This is a nice special case because there's a specific equation that we can use to calculate the wavelengths of spectral lines of the hydrogen spectrum, which is the Rydberg equation. Just a reminder of what photon emission is, let's consider several energy levels. I'll just show three of them here. When photon emission occurs, an electron moves from a higher energy level to a lower energy level, and that loss of energy is accompanied by emission of a photon. The energy of that photon is going to be exactly equal to the energy spacing between the starting energy level and the final energy level. In this case, going from n equals 3 to n equals 1, that energy spacing would be the energy of the photon. And the energy of the photon is directly correlated to the wavelength of that photon. So let's do the first problem. In this problem, we're going to calculate the wavelength in nanometers of the spectral line in the emission spectrum of the hydrogen atom when the electron transitions from the n equals 3 level to the n equals 1 energy level. So in other words, appropriate to the drawing that we have here, we're going to calculate the wavelength of that photon. Here's the Rydberg equation. 1 over the wavelength, lambda, equals the Rydberg constant, r, times the quantity 1 over the n squared of the final level, minus 1 over the n squared of the initial level. And the Rydberg constant has a specific value, a fixed value, r equals 1.097373 times 10 to the 7th meters to the minus 1. So for this problem, n initial is going to be equal to 3, and n final is going to be equal to 1. I'm going to use the Rydberg equation to calculate lambda. So the first thing we're going to do is substitute in for n initial and n final. So 1 over lambda equals r times 1 over 1 squared minus 1 over 3 squared. So since n final equals 1, that's why I have 1 over 1 squared. N initial equals 3, so I have 1 over 3 squared. Now we'll go ahead and evaluate each of those squares in the next step. 1 over lambda still equals r, now times the quantity 1 over 1 minus 1 over 9. All we've done is to evaluate this 3 squared and turn it into 1 over 9. Then we're going to evaluate the 1 over 9, so we'll just do that division. So 1 divided by 9, and then we'll do 1 divided by 1 to get the next step. So still 1 over lambda equals r. 1 over 1, of course, is just equal to 1. 1 over 9 is equal to 0.11111, extending out forever. We'll just cut it off after 7 of them. Okay, then we're going to evaluate the expression in the parentheses. For that, we'll use our calculator. So I've got 1 minus 0.1111111. And that equals 0.888889. Okay, so then we'll just substitute in for that. We have 1 over lambda equals r times 0.8888889, and that just comes from evaluating this expression in parens. The next thing we're going to do is go ahead and substitute in the value of the Rydberg constant, r. So 1 over lambda equals 1.097373 times 10 to the 7th meters to the minus 1 times the 0.8888889. So that comes from here. The Rydberg constant is, of course, right there. The next step then is we're going to do that multiplication on the right-hand side. So we'll go back to our calculator. In this case, we're going to use the scientific notation capability of this particular calculator. You have that on yours as well, but the buttons might be different. So then we'll do 1.097373 and exponent 7 times 0.88888889. And then to get that in scientific notation, 9.754426789 times 10 to the 6th. So we'll go ahead and up here on the right, there's our 9.754426789 times 10 to the 6th that just came from our calculator. And that came from evaluating the right-hand side of this particular equation here. That's where this number came from. The next thing to do is just to do an inversion of both sides. In other words, just flip them upside down. That means I'll turn my 1 over lambda into lambda, and I'll take the reciprocal of the right-hand side of that equation too. So to take the reciprocal of the right-hand side, we'll go back to our calculator. Move it over here out of the way. So I have 9.754426789 times 10 to the 6th. Unfortunately, this calculator is kind of a pain, so I've got to put that in memory. Then I'll do 1 divided by, I'll recall that memory, and equals 1.02517555655 times 10 to the minus 7. All right, so here that is. Now lambda, since we inverted that, that came from here just by doing an inversion. And then the reciprocal of this number is our 1.025175556 times 10 to the minus 7. Now remember, what we were asked to do is to calculate the wavelength in nanometers. We have the wavelength in meters. We need to take advantage of this conversion equality. The definition of a nanometer is 1 times 10 to the minus 9 meters. So now we have to do the appropriate transition. I want to make a conversion factor out of this equation, this equality here. I want to cancel meters. I want to keep nanometers. So I'll put meters on the bottom. I'll put nanometers on the top. So lambda is equal to our 1.025175556 times 10 to the minus 7 meters times 1 nanometer over 1 times 10 to the minus 9 meters. And that gives us 102.517556 nanometers. We've done that conversion now because meters here cancels meters there. Now we didn't worry about digits of precision, so we have to go back and see what's limiting our digits of precision. Turns out the limitation is the Rydberg constant itself. I have 1, 2, 3, 4, 5, 6, 7 sig figs there. So I need to round this to 7 sig figs, meaning I need to cut off and round right there. So my final answer then is 102.5176 nanometers. All right, let's consider another problem that will again be about the emission spectrum of hydrogen. This time we're going to be given the wavelength. We're going to be given the in final, and we need to calculate the value of in initial. It's a little bit more complicated, but just simple algebra. So this problem, one of the spectral lines observed in the photon emission spectrum of the hydrogen atom, has a wavelength of 1003 nanometers. The final electron energy level for this spectral line is n equals 3. Find the initial electron energy level. So the diagram appropriate here is the electron going from a higher state, in initial, we don't know what its value is, going down to in final. All we know is that in initial is some integer number, corresponding to the principal quantum number of that energy level. So here's our Rydberg equation, same one we had before, the Rydberg constant. Now we're going to substitute in for the values that we know. We're going to substitute in for in final. We're going to substitute in for the wavelength. Now, one thing we notice is that the Rydberg constant is in meters to the minus 1, and our photon is in nanometers. So the first thing I need to do is to convert my photon wavelength of 1003 nanometers into meters so I can use it with the Rydberg equation. So let's once again use the definition of a nanometer equals 1 times 10 to the minus 9 meters. So that means 1003 nanometers equals 1003 times 10 to the minus 9 meters. We've simply applied this definition of the nanometer over here. So the next thing then is to substitute that wavelength into our Rydberg equation along with our in final value. So 1 over the wavelength, which is 1003 times 10 to the minus 9 meters, equals r. 1 over 3 squared minus 1 over n squared initial. So this was the wavelength that we just came up with. the 1 over 3 squared reflects our value of n final, which is 3. The next thing we'll do then is we'll divide both sides of the equation here by r, and then we'll go ahead and evaluate that 1 over 3 squared. 3 squared is obviously 9. So we're going to get on the left-hand side now, once we divide both sides of this equation by r, we'll have 1 over 1003 times 10 to the minus 9 meters r equals 1 over 9 times 1 over n initial squared. Now the 1 over 9 comes from here. R, since we divided both sides, ends up on the denominator on the left. The next step is to substitute n for the value of r. So we have the value here. So we'll just do that substitution. The left side then becomes 1 over 1003 times 10 to the minus 9 meters times 1.097373 times 10 to the 7th meters to the minus 1. I've gone ahead and subtracted 1 over 9 from both sides, leaving on the right-hand side just the minus 1 over initial squared. So this r value we've substituted in, that's here. The 1/9, since we subtracted that from both sides, now ends up on the left side of the equation. Now we're going to evaluate the denominator, which is this expression. So we're going to evaluate that. So let's go back to our calculator. So I have 1003 times 10 to the 9th, I'll take 10 to the minus 9 then, times 1.097373 times 10 to the 7th. So that denominator equals 11.0066519. So the next step, we're going to substitute that in. Get rid of our calculator. So here's our 1 over 11.0066519, still minus the 1/9. So we haven't gotten rid of this, it's still here. And then on the right side, we still have minus 1 over n squared initial. All right, now we're going to begin working over in our white space over here. So we'll evaluate this expression. So we're going to work out on our calculator 1 over 11.0066519, and we'll subtract from that 1 over 9. So back to our calculator. So 1 over 11.0066519 minus 1 divided by 9 equals minus 0.0202569555. So here's that, minus 0.020256955, and that equals, still on the right-hand side, minus 1 over n squared initial. Now what we're going to do is to invert both sides. In other words, just flip them over, take the reciprocal of both sides. When we do that, the right-hand side, we'll get rid of the 1 over, and we'll just have the n squared initial. The other thing we're going to do is, since I have a negative sign on both sides, I'm just going to cancel those out and make both sides positive. So I'll do both those steps at the same time. The first thing to do then is to take the inverse of that expression on the left side of the equation. So we'll go back to our calculator, move it over here out of the way. So now I need 1 divided by 0.020256955. That equals 49.3657598. I'll substitute that in. And that now equals n squared initial, because we've taken the inverse. So now we have this. The next step is to take the square root of both sides. That's easy, leaves our n initial on the right. We've got to do this square root on our calculator, so go back there. Calculator over here. So 49.3657598. We'll take the square root of that, just hit the square root key. The square root of that is 7.026077127. So there is the square root on the left. That equals n initial. Now remember that our n initial value needs to be an integer, and I can see that that's pretty close to the integer level 7. So my final answer then is that n initial equals 7.